Okay, so first of all, thank you for the opportunity to give a talk, like this two lecture here at the school, and thank you to the Simons Foundation to funding us all. So that's thanks to the foundation we are here. So, so this talk is more or less the outline has three parts. Okay. I would say that the first two are more like textbook level, so they're really textbook level, and the third one that will be mainly tomorrow, it's more the application of what I will explain today to the case of internal and inertial waves. So in particular, just a warning over this first part, there will be many equations that I will just show. The idea is you don't need to write them down. It's just to show you a bit very different physical system that are basically, they have nonlinear waves, and we can cast them all in the same type of structure, and which will kind of motivate the derivation of kinetic equation. So this is the first part of today, and the second one is, which is also will be quick, just a bit what is wave turbulence in a nutshell, so you can get an idea of cascades or what we are going to show then a bit more analytically what is possible to do. And the second part, which is really textbook level, is how we derive the kinetic equation, which describes the statistics of waves in the kinetic limit. That is when we take the box size going to infinity and nonlinearity going to small, to zero. Okay? So, so the first example, probably the favorite of the collaboration, is the nonlinear Schrödinger equation, which most of you might know. Okay, so it's a dispersive equation, okay, which has a dispersion relation like k squared. Okay, typically we consider cubic nonlinearity. Okay, we will always consider a box of size L for the time being, and periodic boundary conditions. So everything I will say is periodic boundary conditions in the size L, okay? So this equation obviously has this energy, okay? And it's a Hamiltonian system. So if you just take the Fourier transform, just notice that the normalization is like that. There is no L in the denominator. This is a convention that is useful later, okay? Yes, thank you. Okay, if you just take the Fourier transform here in this equation, this term will just give you omega k ak squared, so the Fourier amplitudes, okay? And then there is a quartet term, so there is just convolutions, okay? And now I'm introducing some notations, okay? So there is this A1, 2, 3, 4. A1, it means the Fourier mode evaluated at K1. The sum 1, 2, 3, 4 stands for sum over K1, K2, K3, K4. This K are in the theta d, and delta 1, 2, 3, 4, which appear here, it's a Kronecker delta, which ensures that this is it comes from the homogeneity of the system. Okay, it's basically that I need this guy is a Kronecker delta is 1 if K1 plus K2 is equal to K3 plus K4. Okay, and just also a bit of naming. In this type of nonlinear way, we call it's a four-wave interaction, because you see here where there are in interaction energy there are four wave vectors that interact. Okay, we typically in this case we denoted 2 to 2. Okay, so you have two vectors, K1, K2. Okay, that gets out K3 and K4. So this is the idea of basically if it were particles, okay, that will be the momentum of the particles that are exchanged during the nonlinear interaction. So this is one of the sample that was studied a lot in the collaboration. Another perhaps the most common wave system that you can imagine are acoustic waves. Okay, there are many issues from the theory, but that we can forget for now. Okay, and take the simplest way of the simplest case of acoustic waves. So you have basically Bernoulli equation, okay, and a conservation of the mass. This is a really kind of first course on fluid mechanics. You take perturbations about a flat state, and you get the D'Alembert equation. So waves, which dispersion relation go like K. If you want to cast this system into a more in the same spirit as before, it requires a bit of work. Okay, This is to go back to the 70s to Sakharov and Zagdiv, okay, and well, this is something more recent where we care about the wave turbulence, but for the time being, what the idea is, in all this nonlinear wave system, you will perform several change of variables until you get to the form you want. In this case, you go from rho to phi to some variables a and p with some ad hoc change of variable, then you go to Fourier, you diagonalize the system, okay, and in the end, you get this type of equation. Again, we have an energy that the lower order is omega ak squared, okay, in this case, omega is just ck. And we have this term here, okay, so now we have a coefficient b, 1, 2, 3, which for the particular case of acoustic waves, scale like k1, k2, k3, the whole to the power 1/2, okay? And also for this system, there is the prefactor here, which is 9, square root of 9 speed of sound over 32, okay? This is just a number. So now we cast this system into this nonlinear wave system, which is what we call now 3 waves, okay? So this is just 2 k's that come from, for example, from this delta, again from homogeneity, 2 k's that go to another one, okay? And this is something that we consider. So this is the simplest. Now, another example that was quite popular in like 20 years ago is the elastic plates. You just take an elastic plate, you vibrate it, okay? At the very lower order, you just get this guy here, okay? Which are bending waves, okay? If the plate, if these were the plates, it's just the energy to bending, okay? It's not a drum, not a membrane, but it's an elastic. So you have a relation dispersion that is k squared. So look at here, you have an omega squared. It's a B Laplacian, so this is k4. So it's omega like k squared. E rho is the density of the plate. E and sigma are the properties of the media, okay? Poisson ratio and Young modulus. And a plate has no linearity, that is, you cannot stretch it or compress it, okay? And in the limit that you have a very thin plate of a thickness h, you can go to Landau-Lifshitz, and you see that the system that describes nonlinearly this plate is given by that, okay? So again, if you do a lot of change of variables and go and diagonalize the system, you can again recast the same equation here into this, okay? Here I just use another notation, but they will not last much, so it will be present. So I would call A plus and A minus is just AK and A conjugate. Okay, there's some Hermitian symmetry that you take. But basically, again, you have a wave equation, linear equation for A plus some interaction here. In this case, the TK-QR, that's way more complex. Okay, but still, it's something that is so homogeneous in K, so it gets some powers, and we have this type of system. So what I'm doing now is just giving you examples of very different physical systems that I'm casting into the same kind of description. Okay, and well, what I didn't say for this particular system, you have other type of interaction, the 2-2 that is in NLS, and also it's not trivial at all to see it from here, but you can realize that there are also 3 ways that go to 1. Okay, this is a peculiarity of the system. Okay. So this one is perhaps more interesting for what I'm talking tomorrow. So I will describe it a bit more in detail. It's inertial wave. So now you take a fluid, you put it under rotation. Okay. You obviously here I'm never adding dissipation or external forcing. I imagine that this dissipation is really small, so you have inertial range. Okay. And I'm rotating strongly. I will assume that I don't have geostrophic modes. So this is a work mainly done by Sébastien Galtier. Okay, so the idea is to do the same, to write this equation, which is the Euler equation in the rotating frame, in this way. And Sébastien did it. You do something what's called the helical decomposition. So you look at the eigenvalues and eigenvectors of the curve. Okay, this is for space, and you expand the velocity field into this basis. Okay, which is very nice because you are just as US divergence free. This is kind of the natural basis to expand it. So basically, you plug this guy, you here in the equation, do all the math, okay, and you will get to this equation here, where the linear part is just given by the inertial waves dispersion relation, which is cos. Cos is respect to the vertical angle of rotation, and some nonlinear matrix KPQ, which is just right down here, okay? And in this case, it's again 3 ways interaction, okay? You have the 3 waves here, KPQ, that interact in this way. And by the way, this is the generic interaction that we always have in a kind of a fluid type of interaction. Another kind of the Gaussian system, okay, is the internal waves, okay. Now it is in this Boussinesq equation, okay, and so we have a stable stratification, so that is characterized by the buoyancy field B, okay, and we have Navier-Stokes, so it's coupled with the scalar field, okay. There is a long story of derivation of this equation that goes back to Hasselmann, okay. I'm just citing the most recent one, Vincent Lavar, and we did with him. It's a bit simpler. It's kind of closer to what I'm describing. Here we use a different basis. This I will describe it a bit better tomorrow too. But the idea is the same. You find a good basis where this set of equations looks nicer and simpler. And you can recast it again into this formula, okay, where you have waves and nonlinear interactions, okay? In this case, for the internal waves, so now it's a sinus in terms of types of cosinus, okay? And these coefficients are something you compute again. So this is basically something you do once, and then you're happy. Sure.
What about, for this problem, what about the zero frequency modes?
Yes, are completely discarded. Yes, they have to be discarded. So there is, apart from the work you have done with Claude recently, it's...
But you need it if you want to make a full basis.
No, if you can imagine, so you can imagine that so this is not really what I want to cover. This will be more the subject of tomorrow, okay? But to anticipate, and so maybe it will be a good connection for your talk of this afternoon. You can imagine that this system, okay, you manage and project to kill what is not in the wave component. So it will be the toroidal part. The idea is numerically, it will be simple to do and experiment, okay? For this case, it's particular, but for inertial wave, you can imagine a way of killing geostrophic modes. You put something in your experiment in order to approach. And then it's obviously a problem, but you imagine that, so some of the zero frequency modes are okay because they cannot really exist because of the boundaries of your system, okay, in a real experiment. So this is fine, so it's fine to take them out. And otherwise, you expect that yes, you are really asymptotically in fruit going to zero and Reynolds buoyancy of order 1, this will not grow much.
I agree, in the end, you can get to the waves separately. But
yes.
When you're formulating the problem, you need to have that component, and it's not in what you've written. So
you can imagine that this is a reduced system where I have projected this mode out, if you want. It's just a matter of, I can mathematically formulate to see, I will project the nonlinear terms, so these terms are killed. And this is a self-consistent model which conserves the energy of the waves. Okay, if I do it in that way, it's well set. Whether this is physically relevant, it's certainly in the asymptotic limit, it will be true. But this, you can imagine an experiment where you try to kill toroidal vertical vorticity. You can try to imagine a nice experiment. That is, I agree. Anyway, this will be, I will discuss it more in tomorrow's lecture. Okay. Again, say this is again of type of 3, one type of interaction. So so the idea, why do we call all this wave turbulence? What is the turbulence thing in here? It comes really from the concept of turbulence in hydrodynamics. So this is the very famous picture taken from Uriel's book, okay, where you have in Navier-Stokes turbulence, you have big eddies which will create, excite small eddies and smaller, okay, until you get to the smallest scale of the system where dissipation is efficient to kill them. Wave turbulence is the same idea, okay? You start with waves that have a very long wavelength, okay? And thanks to the nonlinear interactions of the system, you will excite, call it harmonics, or can be, they're actually more complicated wavelengths, at half of the size and smaller, until you reach energy dissipation. And which is the main concept which is in behind all this is the turbulence. If you really can understand to the simplest description of turbulence, that you have a constant flux of energy along the scales, either here or in the waves, okay? Which here is, if you want to be the simplest case, okay, and you say that, okay, the only thing that can govern the physics at such scale is not the forcing, it's not the dissipation, it's just the flux P. So then you do what we all physicists know how to do, is to say, we do dimensional analysis. Under this assumption, just to remind you, so we want to describe the energy spectrum, okay? How much energy we have at a given K. So this has unit of a length Q over time square. What else we have? We have the flux, which is a length square over a time Q. Obviously, we have the wave vector K, 1 over a length. And for the wave problems, okay, we have omega, which is 1 over a time. If in the case of hydrodynamics, you only have P and K, and if you really say I can only use P and K, okay, there is no other escape than P to third K minus 5 third. And this is the simplest way of getting the Kolmogorov spectrum. Now, if you go to the waves, you have to introduce the frequency, okay? So you have an extra dimensionless quantity, okay? Which this time I wrote it like this, okay? So basically, this gives me the units of the spectrum, and this is a dimensionless quantity, okay? Which a priori, I don't know what is the power of this. If I know how the spectrum is scaled with the flux, I could fix it by dimensional analysis, okay?
You don't even know its power, right?
I know it a posteriori, right? After doing the kinetic equation.
Yeah, but it could be a function of that non-dimensional power, doesn't it?
Yeah, of course. I'm a physicist, so I only know about power laws. If it's not a power law, I start shaking a bit. Okay, and for internal waves, for instance, I could apply the same argument, which is kind of should be wrong because this is highly anisotropic, so it cannot do it so easily. But we could forget about anisotropy, which is certainly it's completely wrong, but we will get the same. And if we do NLS, it's even a bit more complicated, okay? Because we have even an extra parameter. So in the T matrix, in the nonlinear part, there was a beta, which was independent of the linear dispersion relation, okay? So there are two parameters, which basically they tell you that you have actually two dimensionless quantities that even with just pure dimensional analysis, if you know how the energy is scaled with the flux, you still don't know how to fix the other one, okay? So the idea of wave turbulence and the strength of this theory is that this allows you to fix all this. So in a nutshell, which when I want to describe a bit later, what you do, you define what is the wave action spectrum, which basically the average of AK square. Okay, let's see what the average is. You can imagine that it's average over initial condition. This is the way we derive, and we take the kinetic limits. We say we'll consider that the linear time that is much larger than the linear time given by the 1 over the frequencies, and which are in a way much smaller than 1 over epsilon square. Okay, and I will look at the time of this order. Okay. I assume something on the initial condition. It's that the phase and the amplitudes are random and independent. And under this assumption, I will just take epsilon as a small parameter and do perturbations in order to get something which is well defined. I first take L going to infinity, so I don't have any discreteness, and then epsilon going to 0. Obviously, in the other way around, it will never work. It will be just a linear equation. And then you can play, of course, different combination of a scaling relation. So the goal of today's lecture is to show you, okay, that in this case, you get something that is well defined, that is kinetic equation, okay? It looks like a bit like the Boltzmann equation, okay, where you have, it's a nonlinear differential integral equation, where I have the information of the nonlinear system contained in the matrix V, and I have these two deltas here. For the four-wave type, okay, I get this different nonlinear, the different kinetic equation, which makes intervene the actually three of this n, which is which make a stronger connection with this picture of the 3 or the 2 and 2 interaction. Okay, you see from this term here that is supported on 2 Diracs. Okay, one that tells you that k is equal to k1 plus k2. So it's basically this picture of the 2 vector has to satisfy this. This is conservation of it will be really related to the conservation of the momentum of the system. And this one here tells you that the frequency has also to adapt, okay? So this defines a manifold, okay, in Fourier space, which we call the resonant manifold. So all the dynamics of the waves is actually it lives in this manifold. Similarly for this case, okay, you have the same, but now there are more waves. So what I will do today is just derive this equation, but I will not derive it completely because it does take many hours. I will just show one term, which is this one there, okay? And the other one, it's the same idea, but much longer. But before going to that, okay, I just would like to come back at the scaling of the energy spectrum with the flux, okay? And this is something, if we assume that this is true, we can already get, just counting here. So energy spectrum is roughly proportional to omega times n, okay? Which is important is the relation between E and n. The flux is the time derivative of E, okay, that I get from here, okay. Here, for instance, in this case, the time derivative of n is proportional to n squared. So E den dtn is proportional to square, and this is proportional to the flux. So the flux is proportional to p 1/2. So from here I get that y should be 1/2 in three waves interaction. If I do the same in the 2-2, okay, I get that basically the flux is proportional to E cubed, so E is proportional to the P 1/3. And that's nice because that fixes one of the exponent. Okay? So if I go back to the table, now here if I completely fix I know everything to say how dimensionally it should scale, assuming that everything works fine, which is this has to be checked case by case. I should have a spectrum that go like this. Omega is proportional to k. It should also work for internal waves, but obviously this is anisotropic, so I cannot say much. For NLS, I did something. I advanced a little bit, but I still get some unknown dimensionally. That the only way to fix it is to do some computations, okay, which I will not really show today. But for instance, the way turbulence theory actually allows us to go a bit farther, not only get the powers, but get the constants that are in front, okay? So this is, for instance, we get that the Kolmogorov constant that here can only be measured in numerics or experiment. In the case of acoustic wave in wave turbulence, it's a number that you compute, and this is a universal result. Here, there are many issues, we cannot do much. And actually, for NLS wave, we can fix the unknown exponent and even find that it was not really correct, and to see what is actually an exact solution of in the turbulent case for the energy cascade. And all these results are exact analytical, and there are no any other assumption than that the physics described by the kinetic equation.
These spectra that you are showing, they are for a certain limit at large scale.
So it's the result that comes from kinetic equation, okay, and always for energy cascade. Okay, I'm reducing today and tomorrow talks to system where I will just mainly focus on energy cascade, not more things.
What does it mean, energy cascade?
Something direct cascade. Okay, so the energy, the flux of energy is constant along scales. Okay, so there is I inject at small k, and will go down to high k. Okay, and I dissipate in some manner, and I'm looking in the middle as usual in turbulence. Okay. And the peculiarity with this log is something that appears in turbulence, in Navier-Stokes, phenomenologically, and here we can actually find it analytically and even find a number there, which is, the evaluation of an explicit formula. Okay, so the idea of showing all this is to kind of tell you that the theory is kind of powerful, okay, and this exponent and this spectrum is something you can test numerically, or eventually for some system experimentally, and it works quite fine.
So to clarify, the nk for the kinetic equation is the wave action, right?
Yes, so nk is the wave action. What it is related to the original problem somehow is related to the amplitude of the waves. The exact formula, it depends on the physical system. It's what comes out from diagonalizing the linear dynamics, right?
The wave action is not the concept quantity. The wave action concept is the equation.
It depends on the system. It's for this case it is, okay. For the other it's not, okay. And so just to make simple, today I'm not talking about cascade of wave action, okay. I will just talk about cascade of energy, kind of ignoring that in another system there are two cascades. Say again?
You have U1 symmetry.
In NLS, yes. So I do have inverse cascade, but I will not talk much because I will.
No, I'm not saying inverse cascade. You always have the number density conserved because of the symmetry.
Yes, you need to have a 1U symmetry in the Hamiltonian in order to get conservation of wave action. And in all this case, you will have an inverse cascade of mass, of particles, or whatever you can call it, depending on the system. Okay?
You quote the formula for the logarithmic correction, and it's not there in the other examples. Is that because you can't compute it in the other examples, or only in this example?
It's a pathology of the NLS equation direct cascade. Okay? It's very specific, so it's really like of a peculiarity of NLS. Okay? For NLS, there is some issue, okay, which brings some divergence, and here there is a cutoff that I need to put explicitly. It's NLS 3D energy cascade, has this pathology. It's not generic, okay? But the point I'm making is this pathology, I can kind of really characterize it for NLS 3D using the kinetic equation and bring an analytic expression for under the energy spectrum, which has a log correction, okay? It's a calculation you do you assume that you have a kinetic equation that describes the physics, and you manage to solve it in the assumption of constant flux. And when you do that, you find this. Okay? It's a calculation, analytical calculation in some asymptote.
I'm wondering whether you could predict that this will occur by just looking at the equations, or whether you have to go through all the steps until you find it. Is there something that you can point to the NLS that's special that generates this logarithmic?
No, it's related to convergence of the integrals. Okay, so you have some divergences that you have to heal somehow, and the way you heal it's putting logarithmic correction because there are very mild divergences. It's very specific to the case. Okay. Sure. So the next slide will be the last slide, and then I will go to the kinetic equation. So if you have general questions, perhaps it's good to raise them now.
So I always wondered about the interpretation of the solution of the initial PDE in the physical space. Because when you have such a power spectral density, which is the integral is diverging, obviously.
Yes, but this is not the real variable in the system. I'm looking like the gradient of my initial field.
Oh, that's the gradient of the initial field.
Yes, for the case of NLS. Okay, for NLS, my field, my microscopic physics is given by psi, right, which is the variable of the NLS equation, and the energy is proportional to the gradient square of psi. So if you want to go to the spectrum of the linear variable, you have to divide by k square. It's still very steep, huh?
It's even less integrable.
Yeah.
And
so this is the whole thing, okay? This is anyway you have to imagine that you have some mechanism at large k that will kind of take out the energy, always, because you need to sustain the flux, okay? And indeed, they are okay. And they have, of course, if you want to fulfill the energy in infinite state, you need to supply an infinite amount of energy in order to have a completely developed spectrum. A bit like the 2D inverse cascade in Navier-Stokes. It's the same spirit. And it's somehow similar. It's very difficult to observe numerically for the same reason that it's difficult to observe the inverse energy cascade in 2D. Good, can I move forward? I think I could. Okay, so let's start. So as I say today, I will consider this setting, okay? And perhaps I should start. I should turn off, so I will just write.
you want to switch off the...
Yes, I will. So this is what I will do today, okay? I will consider this system, okay? And I will start. Okay, so the goal is to derive the kinetic equation in the three-way system, okay? So we consider okay, to make it simple, I will say that it's Hamiltonian, Okay, so I can. It's not a necessary condition. It's just make things a bit simpler, which is described with a Hamiltonian. Okay, which first has the waves, so it will be just some dispersion relation that I don't need to specify. Okay, so that's wave dynamics. And I add some interaction. Okay, and that will be A1, A2, A1, A2. Okay, and I will just get this, just to remind you, okay, and the sum here is over 1, 2, and 3. So sum of over all k, okay, and k's are in 2pl theta d, okay, this is the typical setting. What else? The only bit I need to say, as shown here, is this guy's that will actually make things a bit simpler, 3, 2. Otherwise, I could try to symmetrize it. Okay. I'm forgetting something. And I want to say that this is a small. Okay. So the A's are of order 1. And just a note, this is obviously not the most generic Hamiltonian you can imagine for 3 waves, okay? One could consider something like okay, I have any way, I need that k1 plus k2 plus k3 is equal to 0 because of homogeneity, so I will have, okay? But these terms you can show, it will be clear later, that are non-resonant, okay? So, but what does it mean? What does it mean? That there is, in the kinetic limits, they don't contribute, okay? One, of course, sorry. 1, 2, 3. Okay? The way to understand this a priori is quite easy. As you remember in the kinetic equation, so I can anticipate the result. When I have terms like dk1 to c, this will come with the terms in the kinetic equation, okay? With a delta and omega, that will be omega k. Okay? If I consider terms like the one there, okay, which I will have a 1, 2, 3, then I will get deltas okay, and in the way I'm writing the Hamiltonian, okay, my omegas are positive, okay, so there is no solution for this. Okay? So formally, I should include these terms and do all the calculations with them, get to the end and say, okay, but this term here is 0. So I will not do it. I will say that it's 0, and then you will understand that it's fine. Okay? So this I will write it here. So the equation of motion are simple. It's okay, just a Hamiltonian equation that I need to write, okay? So the Hamiltonian is over there, the linear part is easy. When I differentiate the first term, I have to differentiate with A star. So the first term, the 1 will become K. And I will have a sum over 2 and 3, which I will call 1 and 2. Okay? And I only get the 2 without conjugates. It will be 1 and 2 plus the complex conjugate. Okay? And then I have to, there is the complex conjugate where I have to also differentiate with respect to a star, and I have 2 with the stars, so there are 2 contributions that are symmetric, okay? And that gives you a 2, 1, 2, 1, K2, okay? This is just a simple calc. 1 star, A2 plus complex conjugate, delta 1, K2. Okay, let's check that I keep the same notation. 1, 1, 2, K. Yeah. 1. I think it's okay. No, 1, 2, star. Yep. Yes, that will be correct. Okay, so this is the equation. Okay, so this is a nonlinear equation. We have to supply some initial data. Okay. Okay. Okay, so this is important. At t equal to 0, we assume that all the fields are independent, phases and amplitude for different k. Okay? And then we are going to denote simply ak. Okay? So it's, and we say that are independent for different k's. Okay. If you assume that for the initial conditions, so phases are random and amplitudes are random and independently, that's, you can easily show some weak contraction rules. Which are crucial to make all the statistical computation we do later. What does it mean? So under RPA, random phase approximation, you always obviously have that AK 0. Phases and amplitude are independent, so if we can call it, that will be rho k, let's say AI phi k, which is equal to rho k and this is 0. Okay. Obviously, there are no mean values for the a's. This is kind of this is obvious. If we have AK, AP, will be also 0. Okay. That will be rho K, rho P, I phi K plus phi P.
Rhos and e's are close cousins.
Are look similar?
E's are all the same thing.
They look. They. I will not use it really, so it's just here. Okay. So this, there is no way. If K is equal to P, then I have 2 times the phase, and if they are different, it's 0. Okay. Wow. If I have IK, AP conjugate, then it's different because the phase can cancel, and this is just and the same. If you check, you have A1, A2, A3, A4. You need to have the same number of start and no starts to make it non-zero, and then what you have to do is contract this and this, and this and this, and this will be the sum of 2 points. Correlator square, basically. Okay? Otherwise, that is 0. So this is the setting, okay? And now we want to take epsilon going to 0, okay? Epsilon going to 0, it means that the linear time, okay, which is the period of the waves becomes further 1, and the nonlinear time, okay, which is the given by nonlinearity, goes to infinity. So waves are very quick, and I want to take rid of them, okay? So
Did you say earlier you wanted to take L to infinity first?
yes, I will, but eventually we'll take epsilon going to 0. So I need to remove actually the waves, the linear part. Yeah, just first I will take.
I just thought earlier you made this important distinction that you have to let L go to infinity.
Yeah, but eventually we'll take epsilon going to 0.
Eventually, yeah.
So I need to be prepared to it. Okay, so the way typically, then you go to the interaction frame. Okay, the idea of interaction frame is really the words are borrowed from quantum mechanics as the notation. It's basically typically what we do in quantum mechanics, but everything here is classical fields. And you just simply remove the linear part. A of k will be b of k of t. And you rewrite the equation for the b's. Okay?
You made a quasi-normal approximation.
I have not done.
It's basically the fourth order moments by Brooks for the second order.
No, it's not an approximation. It is exact because of the initial condition makes it exact. Because I'm assuming at t equal to 0 to have random phases and random amplitude that are independent. It follows, okay? It's just an exercise, okay? That the only way of.
Assume that there are no cumulatives.
Yes, I'm assuming independency of the case, phases and amplitude at t equal to 0.
I agree, we can get it from the random phase approximation.
Exactly.
It's still an approximation.
It's a definition of my initial data. I provide the initial data. If you tell me that the data is completely correlated, if you tell me that the phases are typically correlated, they are all correlated, then there's nothing to do. If you have the phases that are completely deterministic, okay, the system will be immediately highly nonlinear.
But I think it's not necessary to derive wave turbulence.
Yes, you can say that. This is a typical approach by Newell, when you get it from multi-scale expansion. Okay, it's kind of similar. You anyway have to at some point show that this cumulant it's small. Okay, but I personally, if you want to derive it, this is way simpler in terms of at least in a pedagogical way.
Well, you're using an additional assumption.
No, this is all the assumptions I'm using.
What do you mean an assumption about the initial data?
This is my assumption about the initial data.
Yeah.
And then, as you will know, then I will, the main question, if this initial assumption will propagate in time, okay? Which is it's the tough question, which I obviously none of us was able to solve, but it was solved recently by Deng and Hani in the collaboration, which is propagation of chaos, which is something that obviously it's far beyond my understanding of how the proof is really going. But here I'm doing not approximation. I give you the detail. This is my initial condition. You like it or not, it's the initial condition. What follows?
You can choose the initial condition such that it's satisfied, but it's not necessary to go on time.
Yeah, I know. You can do a multi-scale expansion in time, and you will get it as a secular term. I know. But this is something then you cannot show in a lecture. It takes a long time to show. Okay. Well, let's follow. So now. Okay, I have the B's, and I need to rewrite the question for the B's. Okay. Right, this is just, it's a trivial exercise. I pass the I to the other side. I don't have linear term. Plus okay, and this is the equation that I will use. So okay, already from here, so this omega is what I define on the slides. Okay, so from here you can immediately guess, okay, that if you take the limit of t going to infinity, this will be a highly oscillating term, okay, and this will not contribute, except if omega k is equal to omega 1 plus omega 2, okay? And a similar thing here. So this already here you can kind of hint that you have the resonant manifold. So this will give you the delta in omega, and this will give you the deltas in k, once I take all the limits, okay? So the idea is we want a statistical description at a time t. At a big time t, okay? Such that if I take the linear time, which is 1 over the frequencies, okay? I want to look at times that are much larger than the slowest period of the waves, okay? But at the same time, not so long, which are smaller than the kinetic time of the system, which I will call TNL. Okay? So what is this guy? So if you see you have an epsilon in front of the right-hand side, you could imagine, okay, just saying, okay, so the nonlinear time is it's the left-hand side divided by the right-hand side. and that will give you an epsilon. But it's not true, because all the terms are random, okay? It's kind of, you can imagine that it's like a random sum of independent things, okay? So in average, contribute to 0. So you will need kind of diffusion. So it will be the square of this term, which gives you the non-typical kinetic time of the system. Okay? So I will look at times of order 1 epsilon, okay? And then epsilon going to 0. This has to be checked a posteriori anyway, okay? But this is kind of the natural assumption. And then you take, so, okay, epsilon going to 0, actually epsilon small. And we expand B in terms of epsilon, okay? So your bk of t will be 0 of k plus epsilon okay? I don't need to go further. And now the idea is you plug B into our main equation star, okay? So I put bk into star, and I will get the following equations, okay? So on the right-hand side, I start at epsilon, okay? So if I look at the order, epsilon to the power 0, okay? That gives me simply that this guy okay, is 0, and then, so that means that it's constant, but t equal to 0, b is equal to the a's, okay, so this is just initial data.
So you don't need to use a multi-scale expansion?
Not multi-scale, it was a single scale. This is the big difference when you do it.
Even though you're aiming for a time interval of size 1/7.
No, I don't have two different time scales in the system. This is the way, it's because of the random phase, the RPA really helps you to do it quickly. Otherwise, you need to really put it inside the B's and get kinetic equation from secular terms, which makes everything way more complicated. But not more complicated, way longer. Okay? This is one guy. The order first epsilon to the 1. Okay? It's easy to compute. This?
So why do you want to do a multi-scale expansion?
Because it's kind of natural. Because usually there are two schools: the Russian and the non-Russian. And so in the Russian was Sakharov, okay, which if you look at the first paper, they were a different setting. So infinite space, so no series, just integrals and multi-scale. And then
Multi-scale, but scale of, you are in Fourier space.
no, you introduce a fast time and a slow time in time. Okay, and then you do it in the typical way, and in order to kill secular terms, you have a kinetic equation. Okay, and this is the approach that is followed by Newell school. Okay, and I think if you assume this random phase approximation, you make everything much simpler, and then the question is to see if you propagate it or not. Which is, the random phase approximation is something that is ultimately related to the weakness of the wave, okay? If the phases are not random, it means that it's really correlated, and you have strong nonlinear structures in the system. If you have strong nonlinear structures in the system, you will never expect to have a weak turbulent description. So it's, I mean, for me, it's totally natural to apply it.
Physically speaking, it's relevant to consider independent Fourier mode.
Is?
It's physically relevant to consider independent Fourier mode, because in the physical space you want stuff to be homogeneous and isotropic, and that would lead to the decorrelation of the Fourier modes.
Yes. So for me, it's something that's quite physical, and it makes all the calculation much simpler.
It will be uncorrelated for sure, but they will not be independent.
Yes, this is what I wanted to say, uncorrelated. Yes, thank you.
Okay, let's go to the. Okay, let's write this one. Okay, exponential of minus I. I will not write all the terms. Okay, it's a bit long and not necessarily helpful. Okay, plus the other one, which has the V1, K2. Okay, so now it's fine. The right-hand side depends only on B0, which I know is initial data. So this I can integrate it between 0 and t. Okay, and just get that B1, sorry, BK at time t okay, something I will call delta t minus omega k 1, 2 of B0 1, 2 plus complex conjugate plus yet the other term. And this delta t is just the integral of the exponential, okay? X. Okay, and this is another formula that I will use a bit later. There is a third blackboard. I think I have space to write it here, so they're all together. And then if you do the same at order epsilon 2, okay, which a priori you also need if you want to derive the whole terms, okay? This is even longer, okay? You have something like of this kind, V, K12 delta, K12. So it's the second order. To typically you will get, for instance, B1 order 0 times B2 order 1 plus other terms, okay? You need them. If you want to derive the whole kinetic equation, you need to compute them, okay? But this is fine because this guy, I know it from 2 stars. Depends only on depends on the initial data only. So a priori, B2, I also know it completely in terms of the initial data. So now, so the goal is to set all the terms in order to gather and compute, which will be an equation for the wave action, okay? Which is simply L over 2 pi, just a normalization factor times ak squared, which is the same as b. And what I want is to write an equation for n in that limit, okay? So I need to compute b. B is a series of different things, okay? But this is something we can compute, okay? So n of k, and this is taking a time t. So that will be L to the power 2 pi, so L over 2 pi to the power d. And I expand the b's. So the b's is b0, bk 0, square, and this I can still develop, okay? Okay, so that order 0 I simply get b sub 0, which I know. Then I get terms, for instance, epsilon, this times this, and finally an epsilon squared that has two contributions. One is when I square this guy, which is the one I will compute, bk plus terms that comes from this guy with this guy. Okay, and we're just focusing in this. Okay, so just a comment, if we look at the average of V, I will not even put the B's, the case, of V0 and V1. In V1, I have two V0s, so if I replace V1 inside this guy, I will concern with three V's. Which are 0, okay? So basically there are no, this contribution here is exactly 0 under RPA, okay? Okay. Here, obviously not, okay, because this is squared and this will contribute, okay? And let's look at this guy, okay? So we will have L over 2 pi okay? If you replace V1, V1 has two terms, okay? Okay, and yet so we'll just compute only one, okay? So this is equal to okay, which we need to compute, okay, if you want to derive the whole stuff, but the derivation is just the same, and this I will call it I1, okay? Is it okay? I'm just doing a brute force calculation, okay? So the more tricky things will come a bit later. So this guy, you can write it explicitly. So it's a product of the formula given by 2 stars. So it's a sum over 1, 2, 3, 4, vk 1, 2, vk 3, 4. I'm just copying this guy there. Delta t minus omega k 1, 2. What else do I have? And I have B00, a B0, B1, B2 plus B3 equal 4, 0, 0, 0, 0. I'm missing some terms, okay, because otherwise it will never end. But this is the idea. And this guy is nice because you know how to compute it exactly in terms of the lower order moment, okay? So B1, B2, B3, B4, to start. This is the initial data. You just need to contract the different pairs. So you need to contract, for instance, this with this, and it with this, okay? And match the index of these two, okay? So you will get, for instance, B1 square. When you match this one with this, B1, B3, but 1 has to be equal to 3. So you will have a delta 1, 3, okay? And you multiply this, you match this with this, and then you with B2 square times delta 2, 4. And then you do the other pairing, which is this with this, and this with this, and you just permute the index. So 1, 4, delta 2, 3. And it's fine because this is the second order moment, which is related to n, which I can plug inside y. Okay. And now this I want to do it, and I have, so this guy gives the same contribution as this. You get a 2. Sum of 1 and 2. Just this I will just write it. 2 pi over L to the power 2d. Don't remember what's doing capital D or small, yes, 2d times L to the power d, delta k 1, 2, this delta here, okay, so yes?
I'll come back to what I was talking about before.
Yeah.
You seem to have applied the quasi-normal approximation.
I have applied the not quasi-normal, the random phase approximation of my initial data.
Yeah,
Which is?
Not just on the initial data, now you've applied it later.
No, I'm applying, this is at time 0. This is, everything here is,
So everything you're doing is at time 0, so how can you go forward in time?
then this is the propagation of chaos that has been demonstrated recently. Okay, so now I'm saying it's kind of my first, if you can imagine like a finite difference. Okay, I want to know how it's n at time big T. Okay, will be n at time 0 plus t times something. This something is the right-hand side of the kinetic equation. That's allowed me to know how will be n at time t. And then, okay, what we will do in physics is say, okay, what was true at time 0, okay, it's now true at time t, so I can do it again. I replace 0 by t and t by 2t, and then I iterate. This is, for mathematicians, that's terrible, huh? And this is the whole stuff of the proof, okay? But orthophasicity will stop there. Okay, I'm getting there, but I'm assuming at time 0. You will have the same time when the multi-scale expansion. You cannot propagate it indefinitely. Hmm?
So we're still at the initial time.
Yes. Look, this is what I'm saying. Here, I have n, k, at time t, which is equal to n of a time t equal to 0, plus what I'm computing now, which will be t times something. Okay? And the something is my collisional integral.
So you're only going a short distance in a slow time.
Yes, it's exactly the same problem with the Boltzmann equation when you try to derive it.
How do you know what happens at x1 squared t of order 1?
Yes, you have to iterate, and this is a very difficult mathematical proof. You don't get any better doing the multi-scale expansion. Okay, you will have the same thing anyway. You cannot control the cumulants at the high order in time. For when you do the second expansion, it's the same. You do it at 0 and at time t, and you cannot get any better. Okay, so what I did here is to multiply. That I should do it with multi-scale expansion.
Sorry, I'm slightly deaf, so I have difficulty in understanding about this thing.
Okay. There is basically two schools, okay? And the multi-scale expansion will not allow you to go any farther in the end. That's okay. And I decided to explain it in that way because it's way simpler than doing a multi-scale expansion that will take me hours more just to derive this term. So if I come back to this term, what I did here, I multiply by this guy to different powers just to get the end, okay? So this, and now I want to take L going to infinity. I can do it now. I'm ready, okay? This guy here this is a delta K, okay? So this will give an integral dk1, dk2, and this gives me a Dirac. Okay, so this is 0 if k is not equal to 1 plus t, and it goes like L to the d, so it has integral 1. So this gives me a delta and k minus k1 minus k2. Okay, and this is my first term. So the I1 is now integral over dk1 dk2 of Dirac of k v and I have this function here delta t of omega k 1 2. Okay, and now it's time to take epsilon going to 0, okay? And now, epsilon going to 0, which is the same as saying t going to infinity. And this guy will actually give me what I need, okay? So if you look at this delta t of x squared, okay? This is just sinus cardinal. Just do the computation, it's just 4 sinus the square of x half over t divided by x squared. Okay. The first thing you can note that the integral of dt of 1 over 2 pi over t is 1.
But this is a bit fast. Why is epsilon going to 0 the same as t going to infinity?
Because capital T is like 1 over epsilon. It's my choice to choose capital T. Remember, I had two times, the linear time and the nonlinear, the kinetic time that I guess that it was, I argue that it was like 1 epsilon squared. So I will take something in the middle, 1 over epsilon. If I get something that is consistent in the end, I'm happy. Okay. So basically, the integral of this guy is 1. Okay. You have that delta t is like over 2 pi when you take x going to 0, that gives you 4 pi goes like 1. Okay, so this guy wait, I'm a bit lost. If I take it at equal to 0, this is x squared. Okay. It's like t for x goes to 0, okay, and goes like 1 over x squared. Yeah. So 0, this is t squared. Okay, right. So this is okay. So this you can start saying that this is a kind of approximate of the delta. So at x equal to 0, it is t, and goes like x squared. This is the envelope, okay? This is for 1t. You take a larger t. Over here, you will have the same envelope, okay? And you start accumulating more and more mass around 0. But the whole getting a total mass equal to 1, okay? So with that, you get this what time is it? We still have like 10 minutes, right? So now it's so it follows this. You can obviously prove it. It's an exercise to prove that this goes like 2 pi t delta of x. Okay, one difference when you do the multiscale expansion that you get a principal value, okay, extra term when you do the large t minute, which actually may be kind of really annoying in some cases, okay. When you assume the random effects approximation, it really helps to do a lot of things, particularly when you have a quasi-acoustic terms. Okay, so now it's fine. So this I1 that I had takes a simpler form, which is 4 pi integral d k1 2 dk 1 2 square delta k minus k1 k2. Another Dirac now in the frequencies, and N1 and 2, okay? And this is the term that I was trying to show, okay? What I did is obviously, for a physicist, it's very rigorous, okay? Okay, but if you want to see the formal derivation, okay? Now let's, now I will just show it a bit later. Okay, where is the? I'm almost done with the kinetic equation. Si, c'est bon, c'est fini. So I have this, and now what if I put if I add all the terms that I did not compute, okay, you get T integral of R K1, 2, RK. Okay, where's this guy here? Okay, this is almost the kinetic equation, okay? So the idea is, okay, you did it from 0. If you propagate the data, okay, now to time t, you will replace 0 by t, and you could repeat the calculation and iterate, okay? So this I could replace t here. This is obviously evaluated at 0, but the idea is now I will replace 0 by t, and I will get it at 2t. And so I'm propagating the initial chaos, okay? And then I will just say something that this guy minus this guy, you can call it a definition, this will be the derivative at time t. Okay? So this is short time, it's a long time, but short compared to the scales I'm looking. And if you do so, which I will write here, you get the kinetic equation, which is, I will write it in another color so it's more visible. It will be just the integral of b of K1 and this is what we call the wave kinetic equation. If you want a rigorous proof that this is true for NLS waves, the only we have, you have to look at to the works of Deng and Hani, okay? There are, which shows that this equation is valid for arbitrarily long time, provided that there are solutions. That the derivation is valid for arbitrarily long time, provided that this equation has solution, okay? I think there are 3 or 4 papers which build the proof. Probably each of this paper is about 100 pages, okay? Which is the idea I think is beautiful, but it's totally beyond my understanding. So I think it's, huh?
And your interest.
I'm interested, and we have heard the talks, we get the idea. We will be impossible to check if they did a mistake or not in the computation. But, it's not our job. We are physicists.
Because you mentioned this, Ricardo,
yes.
he pointed out sort of en passant that actually you can't have real resonances, it's only really the quasi-resonance.
Exactly, so it's so this is the issue.
Do you understand what he means?
Yes, yeah.
Because
so
you're focusing only on resonance.
It's I think the point is, I focused on resonance after I took the limit, right? But I have fixed L, okay, and fixed epsilon. How many resonance I do have? In the best case, is a zero measure, right? It's discrete.
Yeah, anyhow, yeah.
Okay, and then you're taking integral. So it's in the end you understand that it will not really contribute exact resonance to the integral. What is going on that you have quasi-resonant that are close to resonant. Okay, there are infinitely many. Okay, and when you take the limits properly, you need to see that all this will collapse into the resonant manifold that now is continuous. Okay, and the whole stuff is to show that well, those are good, you control it, and which is the other ones which are outside in the system, which are not quasi-resonance, okay, which there are still many terms in the Picard iterates, okay, that those terms, they are not exploding when you take the limits. Okay, and if my interpretation of the proof, what is the difficulty, so that they prove it, so kind of the first nice proof is that they prove it for a fraction of the kinetic time. That was already a big stuff. And then they say, okay, but now you iterate, and each time you iterate, so you have a big number of residuals that you need to control, you do the next iteration, okay, and this will grow exponentially. And the idea is to, I mean, what they managed to do is to bound all this exponentially, then the exponential number of terms that they, a priori you don't know how to control, and to show that properly this goes to 0. How exactly they do that is, I think it's really, we should discuss with them. Yes?
Maybe we
This one presupposes that it's a Hamiltonian system.
It's because it's just easier, but I absolutely don't care. I didn't use it at all, okay? If you see in the dynamic of the equation, I use the equation of motion, that's it. So I don't need it at all. It is nice, because if you have a system and you show that it's Hamiltonian, you get your BK12 with the good symmetries, and then you go to the text. You don't need to do any further calculation. Just go to the textbook and take the formula. If it's not, as for instance is the case of internal wave, you get something that looks like Hamiltonian, but it's not. Unfortunately, you have to do the whole calculations until the end. Repeat exactly what I did.
I agree that rotating theory applies outside,
Absolutely.
but this particular derivation relies on it being Hamiltonian.
Not at all, not at all. I just brought a Hamiltonian to make it more.
You've got this potential energy that drops up everywhere.
No, but look, so it's, if I don't have the symmetry of the V that I can permute indices, okay? So for exactly what I did today, there is not at all, okay? If you don't have the good symmetries of the V's, okay? Instead of having here an R, you will get something different, a Q, okay?
I agree it generalizes, but I was just saying that the derivation is to rely on it.
No, it doesn't really rely. If I don't get the Hamiltonian structure that is given by the V, instead of calling this guy R, I will call it Q, and we have a very similar structure with different collisional matrices. It will be less compact and less beautiful and less adequate for a school.
Maybe we could first thank Giorgio.
Okay, so is there any additional question?
Yeah?
Small remarks.
Sure.
Because what you told is really similar to the two-way space.
Yes.
So this is nothing that was wrong.
Say again. Sorry, it's for the three waves?
So can you take it for an NS?
Yes. So, yeah, so I did it for the three ways because it has typically just one constant quantity, and it's more relevant what I will explain tomorrow, okay? And just that. So the same you can do it for four waves, but not in any case. What they did for NLS, okay? And the peculiarity of NLS that it is that the T1, 2, 3, 4, okay, it's constant. And what you do for NLS, for this 2-2 system, okay, you have to remove kind of a trivial term, okay? Which in the case of NLS is that you have to take care of the nonlinear frequency recognition that arrives at order epsilon, not epsilon squared. For NLS, you just do it playing with the sum in the starting equation, you just normalize it. And it's a constant, their frequency normalization. But you have four waves, so you add the constant to each, you don't see it, and it's easily fine. In other systems, like MMT or four waves, water waves, when you have a T1, 2, 3 that depends on K, the frequency normalization is less, it depends on K, and it's certainly way more difficult to deal. Okay?
And I mean, the reason why I like contribute and I made it in that is because it also has interpretation methods theory complex.
Yes, yes, it's 2 that goes to 1. So and the four ways will be a bit more weird in terms of particle physics.
So my curiosity was which type of channel I using when I look at physics.
Which type of V1, 2, 3? It's the one that comes from the physics, from the microscopic equation. Okay? It can be, if you look at acoustic waves, okay, it will be as simple as, for acoustic waves, if you do the proper limits and you do it in a good way, your V1, 2, 3 is just the square root of K1, K2, K3. For acoustic waves, super simple. You do it for inertial waves, for internal waves, it expands quite a lot, but it's just in some limits are homogeneous function of the case, and you can do calculations. This is the physics. All the physics is encoded here, and then the omegas which are inside this R. But it depends problem to problem. You need to compute them.
Okay, so we'll stop here. Thank you, Giorgio, again.